This is 6-3, the beta lesson. And this is new, okay? Shape, center, and variability of a binomial distribution. Well, this is the center. This is the variability or the spread. So how do you get the mean? It would be the number of the sample size times the probability of success, n times p, and the step will be n times p times q. That'd be the variance. Take the square root. What's q? Q is one takeaway p. So it'd be, well, not sample size, but trials. Trials times the probability of success. Trials times success times failure. The square root of that. And that made me think about all these standard deviation algorithms that you have been presented to you, and how can we keep them straight? So you don't need to do this. I hope everyone has a copy of the formula sheet. All right, not with you right now, but you have a copy. So if we go there, here is, right, on the front page, here is the first formula for standard deviation. Remember when you would divide by n, take away 1, and that's, we still haven't explained to you why we divide by n, take away 1. We'll get there. But this was how far each term is from the mean. The negatives are going to work against the positives, so we square them, add them up, divide by n, take away 1, which they wrote is multiplied by 1 over that, take the square root. So that's the first thing you saw in terms of a measure of variability. Then if we scroll down here, for a probability distribution, we have this on the second page, where it tells you the variance. You didn't take the square root on the formula sheet. The variance, which is what? The sum of how far each term is from the mean, and they're using mu there because it's a probability distribution, so sum of list 2 has to be 1, so you have everything accounted for. Square that and multiply by the probability of that event occurring, and then to get the standard deviation, you would take the square root of this. So there's 2 different ones. And today you're getting a third different one. So this only works, right? You have to say, well, which time do I use it? That's what you have to kind of get your mind around. So here's the last one so far. Sigma of x, where we have the square root of n times p times 1 takeaway p. Binomial. This is a heading. This is under the binomial heading. Okay, so you have this sheet, and when you first start doing this stuff, I get it. You got these different formulas, and I'm trying to keep them straight. You can use the formula sheet. By the time we get to May, you can't turn it back to the formula sheet, we would run out of time. Make sense? So you're just trying to get, all right, this is when I use this one, this is when I use that. So the headings are here. That's binomial, which is what we're doing today. Scroll up. It's the probability distribution. And then on the first page, the original one for standard deviation. So, here we have this algorithm, which is n choose k. Now, let's make sure we understand each other. Because on your test, we don't use this. This is what you're used to. On your test, College Board uses this. That's the way it's the same thing. for synonyms. This means N choose K. Kind of an older way to write it. That's what it's going to look like on the assessment. Okay? Which is it's a combinatoric, it's a combination. Because if we say this is the probability something could happen, we multiply it by each of the ways it could happen. It could happen on the first try, the second try, the third try. Success raised to K. Because the exponents are a shortcut for multiplication. How many successes? Failure raised to N take away K. Because there's N trials, you have K successes. Like if there's 8 trials, you get 3 successes, and you have 8 take away 3 failures. Now, this is new. Think about what this is saying. This is a condition. This has to be met. The population has to be greater than 10 times the sample size, where you have an issue. Now, we will spend a lot of time on conditions when we get to the spring. But here's what this means. If we're doing a binomial distribution of some real-world data, the population has to be greater than 10 times the sample size, because in real-world data, we're doing it without replacement. Like we choose someone, we don't put them back in the pot. They can't be selected a second time. But the theory, ready? In theory, this expansion we use for binomials with replacement. So that's a contradiction. It won't matter, it won't affect your answer substantially as long as your population is more than 10 times the sample size. See, because you're going to have an error here because you did this, you sampled without replacement and you use an algorithm that's with replacement. But if your population is large enough, your error is going to be something that will be well past the decimal point, won't even notice. And it's kind of counterintuitive because we've been telling you for sampling, you want to have a large sample. And the point here is, you don't want your sample to be too big. Because if it's too big, we're going to have a problem between with and without replacement. So it's not just, you ready? It's not just enough to say, get the biggest sample I could possibly afford. When you get your mind around this, there's potentially a problem with your sample being too big. Okay? So we're going to pause the video. That's all there is to that. You're doing one problem. Number 97. Okay. And the question says, there's a 9% chance of the call reaches a live person. Find the probability that more than 12 calls are not complete. So I said, okay. This is, I went binomial, cumulative. 15 calls, 91% is success, because we're looking at successes being not completed. Up to and including 12 gives you 14.5%. So one take away that would be more than 12 were not completed. 13 or 14 or 15. Make sense? So you get this answer. It's way easier to do it from the context of the sum of the probabilities has to be 1. But really what was asked, if we did it the long way, it would look like this. So you see what the answer is. It's 85%. What they're asking you is, don't you do this because it'd be kind of silly. 15, choose 13, the probability of success is 0.91, meaning not completed. Not completing 13, the probability of failure is 9%. You did complete the call. So if 13 were not completed, 2 were completed. But then you have to add to that. Math. (15) choose 14. There is no easy way to copy and paste this. Times 91%, carried 14. And again, I don't want you doing this, so I don't really care that this is running off the screen, because I don't want you remembering this. .09, caret 1. I don't need the 1, but just to see how the algorithm works. Plus (15) choose 15. Now, 15 choose 15 is 1, so you don't need it, but you're better off being consistent here so you see what's going on. 15 choose 15, 0.91, caret 15, and you're done. But just to be thorough, 0.09, caret 0, there's the same answer. But you see how inefficient that is to type all that. It's way easier to say what isn't included would be up to and including 12. And since they all add up to 1, just do 1 take away the sum of 0 to 12. So what we were asked to do was go to distribution, ready? Careful, you're choosing the C, because you want them to add up all the things up to and including 12. See, if you typed P, if you typed A there, you got the P, and you did 1 take away that would be everything except 12 successes. So you're going to get an answer, and that answer is going to be one of the multiple choice selections, but you have to use your numeracy skills here. So we click on that and say, okay, we've got 15 trials. The probability of success is 91% because we're saying that we don't get the call answered. And we're going up to and including 12. And you see how those two are going to add up to 1. We just do 1, subtract second answer, which is way more efficient than adding up. 13 plus 14 plus 15. Okay? What's the expected number? Well, what's the center of this thing? Now, right? We're switching now. We want the expected number. You've got to be careful. Because B asks, interpret X. And X, when you go to the question, is the number of calls that are completed. So now we're going to switch to the probability of success is 9%. So it's N times P, 15 calls times 9%. We expect 1.35 calls to be completed. You got to think about this. That's impossible because this is discrete. You can't have a fractional value as part of your sample, but the center is based upon that. The center is 1.35 calls. okay? Even though you couldn't possibly get the center. And what's the step? N times P times 1 take away P. So here's the step. In sets of 15, the step only holds for groups of 15 calls. It's going to vary from the center by a little over 1 1/10. Okay? So this distribution, the probability of success is only 900, so the distribution is going to be skewed right. Makes sense? You can imagine the tail going to the right. So that's that for the beta lesson. 2 more parts to go to 6.3.